Welcome to another explainer. Look, today I need you to put on your detective hat. Forget literally everything you thought you knew about rote memorization in chemistry, because today we're becoming chemical detectives. We're going to learn exactly how to look at a completely unknown substance, interrogate it using some very specific chemical reactions, and totally decode its true identity based purely on how it behaves. Let's get to work.
Okay, let's dive into our roadmap for this investigation. First up, welcome to analytical chemistry. Then, clue 1, color of salts. After that, we've got the alkali interrogation, followed by the excess reagent twist, and we'll wrap the whole thing up with metals and amphoteric oxides.
Welcome to Analytical Chemistry. Step 1 in our investigation is getting the ground rules straight. We really need to shift our mindset away from just staring at numbers on a page, and instead start hunting for unique chemical fingerprints. Now, our main tool today is qualitative analysis. You got to notice that word, qualitative. We are absolutely not doing quantitative analysis today, okay? We don't care about the amounts, the weights, the percentages, none of that. Qualitative analysis is purely about identification. We're figuring out what an unknown substance is by running chemical tests and just making really careful observations. Specifically, we're looking at the color and the solubility of the precipitates that form when we add our testing chemicals.
For these tests, we've got two primary interrogation tools in our arsenal. First, we have sodium hydroxide. That's our strong, heavy-hitting alkali. And then we have ammonium hydroxide, which is our weaker alkali. Basically, by dropping these into solutions of unknown salts, we literally force the salts to react and reveal exactly who they are.
Moving on to section 2. Clue 1. Color of salts. Because, before we even add a single drop of our chemicals, a good detective always uses their eyes first.
The periodic table actually gives us a massive cheat code right off the bat. If our unknown salt is made from normal elements, so those are the guys in groups 1, 2, and 13 to 17, like sodium, calcium, or aluminum, the salt is generally completely colorless, clear as day. But if our salt contains transition elements from the middle block of the table, groups 3 to 12, those are almost always brightly colored.
And this brilliantly illustrates exactly what we're looking for. These 3 transition metal cations are the usual suspects. They pop up constantly. If you see a blue or green salt, boom, you should immediately suspect copper 2. If it's a pale green, you're most likely looking at iron 2. And if it's this rusty yellow or brown color, iron 3 is for sure your prime suspect. You really want to memorize these 3, because they are the absolute bedrock of visual chemical identification.
Section 3. The alkali interrogation. All right, we've looked at the color, so now it's time for the active part of our investigation to kick off. We follow a very strict 3-step standard operating procedure for this chemical interrogation. Step 1, we take our unknown salt solution and we add our alkali, so either the sodium hydroxide or the ammonium hydroxide drop by drop. Step 2, a solid substance, which we call a precipitate, is going to start to form and kind of fall out of the solution. We carefully observe its color, and then step 3, we just keep adding that alkali until it's totally in excess. We do this to check if that solid precipitate dissolves back into the liquid or if it stubbornly stays solid.
Now, when we use our strong alkali, sodium hydroxide, we get some very specific chemical fingerprints. Don't sweat the complex formulas here, just focus on the pattern of the colors. Iron 2 drops out as a dirty green precipitate, iron 3 turns reddish-brown, copper 2 forms a really beautiful pale blue solid, zinc gives us this gelatinous white substance, kind of like a clear, jelly-like white, and lead produces a dense, chalky white precipitate. Literally, just by matching these colors up, we can nail down the identity of our unknown salt.
But hold on, what happens if we switch out our interrogator? Instead of the strong sodium hydroxide, what if we use the weak ammonium hydroxide? Does the whole story change?
Well, let's compare the two directly. For iron, copper, zinc, and lead, the initial colors of the precipitates are actually exactly the same. The major difference? It's calcium. When we add our strong sodium hydroxide to calcium, we get a white precipitate. But when we add our weak ammonium hydroxide to calcium, absolutely nothing happens. No precipitate forms at all. Why? Because ammonium hydroxide is just too weak. It doesn't have enough hydroxide ions to force the calcium out of solution. And honestly, that is a huge clue for identifying calcium in the lab.
Section 4. The excess reagent twist. We are now officially entering the trickiest part of analytical chemistry.
This is the part that totally catches students off guard, but as chemical detectives, this is where we really earn our badge. Remember step 3 of our procedure? Adding the alkali in excess. We force the salt to form a solid, colorful precipitate. But what happens if we just keep pouring the alkali in? Do the solids stay solid? Well, most of them do. Iron 2, iron 3, and calcium remain totally insoluble. But for a select few, something pretty dramatic happens.
Now, what's really interesting about this is the exceptions. If you have zinc or lead and you add excess strong sodium hydroxide, that white solid completely dissolves back into a clear, colorless liquid. They actually form complex, soluble salts. If you use the weak ammonium hydroxide, zinc still dissolves. But the absolute star of the show here is copper. If you add excess ammonium hydroxide to that pale blue copper precipitate, it dissolves and transforms into this stunning, deep, inky blue solution. It's wild to see. And I literally cannot stress enough how important these specific exceptions are. Previous exam questions, high-order thinking problems, they almost all revolve around this exact excess reagent twist. They're going to ask you specifically which precipitate is soluble in excess ammonium hydroxide but not sodium hydroxide, or vice versa. Knowing these dissolving tricks is pretty much the key to mastering this entire topic.
Section 5. Metals and amphoteric oxides. For our final act, we're zooming out a bit and expanding our investigation. We're moving away from just salt solutions in test tubes, and we're looking at how our alkalis react with raw metals and their oxides. To get this, we really need to introduce a new term, amphoteric. Think of an amphoteric substance as being completely two-faced in the chemical world. Normally, acids react with bases, right? But amphoteric oxides and hydroxides, specifically those of zinc, lead, and aluminum, they play both sides. They can act like a base when they meet an acid, but they can also act like an acid when they meet a strong alkali. And they yield salt and water in both cases. When we treat these materials with hot, concentrated alkalis like sodium hydroxide, we see a really fascinating contrast. If you take the raw, pure metal, zinc, aluminum, or lead, and add the alkali, you get a salt, sure, but you also get active bubbling because hydrogen gas is being liberated. However, if you take the amphoteric oxide or hydroxide of those exact same metals, you still get a salt, but the byproduct is just liquid water, no gas.
And the salts that are formed during these reactions, they have some very unique, kind of tricky names that you'll definitely need to recognize. When zinc reacts with sodium hydroxide, it forms sodium zincate. Lead forms sodium plumbite, and aluminum forms sodium aluminate. These are those complex soluble salts we were hinting at earlier during our excess reagent tests.
So, the crucial point really comes down to mapping out exactly how these three specific metals, zinc, lead, and aluminum, and their oxides behave. If you want to totally conquer this section of analytical chemistry, burning these exact patterns into your brain is absolutely the way to do it.
Which brings us to the end of our investigation today. Let's test your new detective skills with a final question. Imagine you're standing in the lab. Your unknown salt creates a pale blue solid. You keep pouring in ammonium hydroxide, and suddenly that solid dissolves into a brilliant, transparent, inky blue solution. What is the culprit's identity? Well, if you said copper, you are spot on. You've just decoded your first chemical mystery. But remember, test tubes are just the beginning. These exact same deductive principles are used every single day to solve real-world mysteries in forensics, toxicology, and environmental testing. Thanks for joining me in the lab today, and keep looking for those clues.